All right, my friends. Just a little bit about the test. There's a few people that haven't taken it yet because of various emergencies, so I'm not going to say anything about specific test problems. I'll make a video going through each question of the test and explaining how to get the right answer and make that available to you. Let's see, the average score was like an 83%. The median score was 88, so that's actually like really good. So historically, well done. If the test didn't go well for you, I have a few suggestions. If it did, keep doing what you're doing. Don't let up. And I think that's all I have to say. Oh, inevitably, there are questions after the exam. How do I put in context how well I did? And that the answer to that is not simple, so I'll try to explain as best I can. First of all, I make you the guarantee in this class that you're going to get the grade that you earned. So it's never going to be harder to get a B plus than getting 87% of the points. It's not like if the average is too high, I'm like, dang it, I have to now make it so that a 97 is an A. We're not going to do that. That's mean and inappropriate and all that stuff. So basically, you get the grade that you earn. Now, if the class performance justifies it, I can lower the standard cutoffs that are listed in the syllabus. Historically, for example, the cutoff between C minus and D tends to be substantially lower than 70%. So, and those cutoffs tend to be lower in the lower 50th percentile, or the lower 50% of the class than the upper 50% of the class. So, if you got a 60 on this exam, you don't need to be thinking, oh my gosh, I'm failing the course. But you should be thinking, okay, I want to improve. So if you want to sort of know where you stand, sort of think about it in that way. It's difficult for me to say where the cutoffs will be at this stage of the class. I never know that until the very end. I have a guideline from the department that tells me about historically what the GPA average tends to be in the class at the end. And so based on that, I can lower the cutoff somewhat in the end. But for now, I guess, yeah, not sure. I saw a hand. Go ahead. No? Nobody? Yes?
So if I heard you right, the difference between, so a C minus to a D, that cutoff moves a lot more than like A minus to A.
Right, yeah. So in general, historically, the cutoff between C minus and D moves downward more than the cutoff between, say, A minus and A. Usually I round up, so you don't need to send me emails at some point saying that I have a 92.773 and could you please give me the additional 3 points? I tend to round up anyway, so I got you, don't worry. Okay? All right. So with that in mind, we're moving on to chapter 4, and this is fun because we get to talk about molecular shapes. So I'm going to bring up an app that was designed by a guy named Theodore Gray. He's written a couple of books about chemistry. One is called Molecules. You can get the app. It's kind of expensive, so I don't recommend it unless you're a chemistry nerd like me. But there's all kinds of stuff in here. But the funnest thing is this gallery of wiggling molecules. Nope, that's not what we wanted. Nor is that. Come on. There we go. Right there. So there's a kind of computational simulation of molecules that's called molecular dynamics. And this basically treats atoms as being, atoms and molecules as being charged points connected by Newtonian springs with various force constants for bond vibration and bond angle distortions and so on. And they have incorporated that kind of calculation into this app. And you can look at a number of molecules and see sort of what their shapes are in as a function of time. And so here, you guys see that okay? Here is the molecule ethane, and it's just sort of wobbling around there. And the extent to which it is wobbling around depends on what we've got down here at the bottom is bath temperature. Now, you remember how I told you kinetic energy has to do with how fast molecules are bumping into each other, how fast they're moving in solution. It also has to do with how fast their bonds are rotating / vibrating. So what we're seeing now in the bath temperature, or the average kinetic energy of the molecules, is about 50 Kelvin. So this is moving around a lot more slowly than it would be at room temperature. But you can see there's vibrations of those carbon-hydrogen bonds. You can see that the distance between the two carbons is changing a little bit. And you can see that the bond angles are wagging a little bit. And then if you look down individual bonds, you can see the two carbons are sort of rotating somewhat relative to each other. The purple stuff represents electron density. And we can look at this in a space-filling way, which gives you a better sense for actually the amount of space this molecule is taking up. Okay? So I'm going to maybe slow this way down. Ooh, absolute zero. No, it only lets us get to 4 Kelvin. Oh, no, there we go. Even at absolute zero, there's still a little bit of wiggling in the molecule. Zero, it's called 0 point energy, but we've basically frozen that out. All right, so let's talk about molecular shape, right? You have, first of all, bond distances, which will be the distance between carbon and hydrogen, or the distance between carbon and carbon. Then you have bond angles, which you've learned about and we've talked about. This one's 109.5. These are the angles expected for an sp3 hybridized carbon. So bond distances, bond angles, but there may be one other quantity you haven't thought of yet, and that is something called a dihedral angle. Okay? A dihedral angle is where you're looking down a particular bond and you measure the angle between an atom in the back, an atom bonded to the carbon in the back, say this hydrogen here. We're looking at this bond, and we're measuring the angle between this bond, between carbon and hydrogen in the back, with this carbon-hydrogen bond in the front. Okay, now dihedral angles are actually vector, it comes out of vector math. You basically take, if you define this vector and the vector in the back, you take the cross product of those and you can calculate the angle between them. We're going to do no such thing in this class. We're just going to do it by eye. And that dihedral angle is 180 degrees, right? So we'll introduce a term for two bonds that are 180 degrees from each other with this dihedral angle. That is the angle between this hydrogen in the front and that hydrogen in the back, comparing these bonds. We'll call that anti or trans. So those protons are anti to each other. Okay? In contrast, you can see that if we compare the dihedral angle here between the proton and carbon bond in the back, and then this carbon-hydrogen bond in the front, that dihedral angle is about 60 degrees, okay? And we'll call that gauche, or from the French, I think meaning left, and I don't know why we choose that word, but, and we're not using it in the snooty sense of, oh, that's so gauche. I don't even know how you would use that in the snooty sense, but in any case, this proton is gauche to that one. Go ahead.
So does gauche mean 60 degrees, or does it mean like the most evenly?
Gauche means 60 degrees, means a dihedral angle of 60 degrees. G-A-U-C-H-E. You got anti and you've got gauche. All right. Yeah.
You said there was anti and trans in this also?
You can call it anti or trans.
Oh, it's the same thing.
Yeah.
Okay.
Yeah. These two, this carbon-hydrogen bond in the back and this one in the front, those are either anti or trans to each other. Either term is fine. I'll use both interchangeably. Okay, other questions? Yeah.
Can you say the gauche just one more time?
Gauche, yeah, it means a 60-degree dihedral angle between this carbon-hydrogen bond in the front and this carbon-hydrogen bond in the back. So if you do the vector math, or actually even if you just look down this bond, the angle between those two lines is 60 degrees. Okay? Yeah.
If you put something really big on there, like a bromine in the front,
Yeah.
it would still be 60 degrees from that carbon in the back for that hydrogen.
So if you put something really large here, would that tend to distort things? It can affect things, and we'll talk about how that works. Okay? Other questions? Yeah.
Gauche and trans, and like, does that refer to the overall like carbon how it's rotating?
Oh, good question.
Atoms bound to the carbon?
Yeah, so gauche and anti or trans are relative terms. You have to specify the two atoms you're talking about. So I could not look at that molecule and say that molecule is gauche or that molecule is anti. Instead, I would have to say these two hydrogens are gauche to each other. Yeah, or these two are anti to each other. Okay, others? So this view of this molecule where we're actually looking down, we're sighting down a carbon-carbon bond, that view we call a Newman projection, presumably named after the person that decided it was a good idea to look at molecules this way. And we will get good at actually drawing these kinds of things. But I want to now talk about rotation around the carbon-carbon bond. One thing I could say at this point before we move on is that dihedral angles do have signs, mathematical signs. It actually comes out of the vector math. So we're not really going to worry about that or what the sign convention is. It turns out that, See, I don't know the sign convention, but you guys probably don't care. That's fine. Whoops. Now we've gone and ruined everything. Right. Do you see the proton in the back here is on the right-hand or clockwise side of the proton in the front? That's a plus 60 dihedral angle. And on the other side, this is a minus 60 dihedral angle. I'm realizing those protons in the back are kind of hard to see. So this is a this is a minus 60 dihedral angle. This is plus 60. That's not going to matter. I'm never going to quiz you on that, but in case you want to know, there is.
Is it important?
No.
Like,
Do I know
science-
it?
I mean, science in general is important.
How arrogant was that? He asked me, is it important to know? And I'm like, do I know it? I clearly don't know all the things that are important. But what I'm saying is I don't care about it very much. And so you don't have to worry about it at all. All right, so let's turn up the temperature again on this thing. Get it going again. Whoa. Room temperature is about 300 Kelvin. So you can see we've got quite a lot of bond vibration. And the molecule's moving around enough in space that it's difficult to maintain sort of a Newman projection view. But what I want you to see is that we're getting not only vibration of bond distances and distortion of bond angles, but the two carbons are starting to twist relative to each other. Okay? But you can see that most of the time they spend... do you see how that carbon in the front is rotating and it's almost like it's bouncing back and forth? I need to slow down the simulation, get to a little bit of a lower temperature so we can... The other thing we can do is slow down how fast the simulation's going. All right. The equilibrium geometry for this molecule is the one in which each hydrogen in the front is gauche to two other hydrogens in the back. We call this conformation a staggered conformation because, as I said, each group in the front is gauche to 2 groups in the back and anti to 1 group in the back. In contrast, there is a conformation called the eclipsed conformation that is a high energy transition state. It's a maximum in energy, so it's not populated very much. And to see it, I'm going to take a proton in the front and I'm going to, yeah, see, it doesn't want to do that. I'm going to twist a little bit. And I want you to observe what happens. I'll take the proton in the front and I'm going to spin it around. And I want you to observe what happens as we start to, okay, did you see that? I give it enough energy to spin around, and then as it starts to slow down, you reach a point where it looks like it hits some barrier and then goes back. You see that? Okay, the barrier has to do with the conformation where the dihedral angles are all 0. And that's pretty hard to come up with in this program because it's a high energy transition state, and so you can't see it for more than just a little bit.
Decrease the time.
Yeah, we could, well, whoa, yeah. There it went. All right, yeah, so I don't know. I think I'm going to break it, actually. All right. But the idea is that I can rotate around this carbon-carbon bond, but there's a barrier to rotation. You have to go up in energy to rotate through the conformation where the hydrogens are lined up with each other. All right, and you can tell that's the case. I'm going to speed up the simulation again. You can tell that's the case because as I spin, for a while we're going fine, and then you can see that we just sort of knocked into something and it went back down. So the energy minimum is to have all of those carbon-hydrogen bonds gauche to each other, gauche to 2 other hydrogens and anti to 1. All the dihedral angles are either 60 or 180. And that's the energy minimum. And if you make it so all the dihedral angles are 0, that's a high energy intermediate. Yeah?
So I think that the staggered has the gauche, that's pretty specific.
Yeah.
Is eclipse just when you're kind of breaking that gauche transformation? Is there any like specific, what's the word? I guess limits that it needs to be at to be eclipse, or is it just?
So the question is, I guess your question is, so, oh, there it was. There was the eclipsed for just a split femtosecond.
That would go on top of each other.
Where they're on top of each other as you look down that bond. Okay. We could, maybe the app Spartan will let us actually see that eclipsed conformation. I don't know.
And that repulsion, is it electrostatic or electromagnetic?
Good question. Yeah, so unfortunately, this is not going to let us see that eclipse conformation, but the eclipse shape would be if we rotated this carbon in the front such that all the carbon-hydrogen bonds in the front were overlapped with the carbon-hydrogen bonds in the back. Now, what is the origin of that repulsion? And let's talk about that. So if we go back to this molecule, you can see the purple represents the electron cloud. Okay, and in this staggered conformation, the electrons associated with the carbon-hydrogen bond in the front. Let's see, I need to turn the temperature down again. In this staggered conformation, the electrons associated with the carbon-hydrogen bonds in the front, if they were eclipsed with the carbon-hydrogen bonds in the back, we would get more repulsion than we do. It's just electrostatic repulsion. I think probably we've maybe done enough of what we can do just with the models, and now I want to talk about how to actually draw these conformations, and we'll talk more about it. Go ahead.
My question is, like, is there a specific angle that we're looking for? Do we quantify that as eclipse? Staggered, like 10 degrees or something.
The eclipsed conformation, I guess, just refers to where the dihedral angles are 0.
Okay.
Yeah. So I'm going to draw the molecule ethane from the side, sort of as we were looking at it. And this, I'm drawing it currently in the staggered conformation. If I drew it from the side in the eclipsed conformation, you could see how all the carbon-hydrogen bonds on the left-hand side carbon are lined up with the carbon-hydrogen bonds on the right side carbon. If we, so to draw a Newman projection, we're going to sort of lean our heads down, put our nose in the page pointing towards the bond that we're looking at. And then, of course, I always waste time on this. I cannot resist. Sorry if you hate it, but I don't care that much. I mean, I do care, but not enough to change my behavior. So our evil Sith eyes looking down this carbon-carbon bond. For those of you anxiously awaiting the premiere of Obi-Wan Kenobi, I'm just going to say that I am not really okay with the fact that the Grand Inquisitor's eyes are not glowing yellow. Yeah, okay. So this is the staggered conformation. As I said before, the terms we will use to describe dihedral angles are relative terms. So these two protons are gauche to each other, and the dihedral angle is 60 degrees. In contrast, the angle between the purple proton and the yellow proton is 180. Wow, that's a weird way to write that. 180 degrees, and we'll call the relationship between those two anti or trans. Okay? So the name of the conformation is staggered, but we can describe the relationship between two protons, one in the front and one in the back, as being gauche or anti. All right? The circle here, you don't actually need the circle. The circle just represents the bond that we're looking down. You can see the carbon in the front, but not the carbon in the back. Any questions about that Newman projection thing? Yeah?
For the front carbon, is that typically the center point?
That carbon is represented by this center point. Yeah, just like in all skeletal structures. Yep. Okay. The eclipsed conformation is a little trickier to draw, and sometimes you have to sort of, I don't know, distort it just a little bit. So I'm going to draw the carbon-hydrogen bonds in the front. And then in the eclipsed conformation, all the dihedral angles should be 0. So technically, I could draw the ones in the back and it would look like this, but that's not particularly helpful or informative. So the way, I'm trying to undo all of that. The way we do this is I'll just draw the bonds slightly offset with the understanding that the dihedral angle here is 0, and this is the eclipsed conformation. Okay? All right. So the staggered conformation is a minimum, and the eclipsed conformation is a maximum. And so I'm going to show you sort of an energy diagram of how the energy of this molecule changes as we rotate around this carbon-carbon bond. Okay? So let's start with just this staggered conformation. I'm going to call it staggered conformation 1. And it's in equilibrium with a second staggered conformation, And in the second staggered conformation, the blue proton is going to be anti to the purple proton. So that in going from staggered conformation 1 to staggered conformation 2, we have rotated 120 degrees around the carbon-carbon sigma bond. All right? And in that process, these two staggered conformations are equal in energy, right? They're both staggered conformations. In fact, I've pretended that we can tell these protons apart, but we can't. But to get from one to the other, they would have had to pass through a high energy transition state in which blue proton was eclipsed with this other proton in the front. So I can draw that eclipsed conformation. And it's going to look something like this, with purple proton here and blue proton there. We'll call this eclipsed conformation 1. And so there's an energy barrier between, because eclipsed conformation 1 is a high energy transition state. And you can signal that in chemistry with a little bracket and a double dagger to indicate that that's a transition state. What do I mean by a transition state? Well, if we made an energy diagram, energy on this axis, and then on this axis we're going to put dihedral angle between purple proton and blue proton. And let's just say here it's 60. Here it's 120. And then here it's 180. And what we would see is that energy goes up to a maximum at 120 and then drops back down to the same minimum at 180. That's kind of not that great, but we will try again. Okay, but I meant for those two to be equal in energy. All right, close enough. So the staggered 1 conformation and the staggered 2 conformation are equal in energy, and they are both lower than the eclipsed conformation by about 3 kilocalories per mole. All right. Questions about that energy diagram? We'll be sort of doing this a lot. Go ahead.
For the energy diagrams on the homework, sometimes there's it's not all hydrogens, obviously. So
right.
It can be backwards. Does it matter which way we rotate, or is there a preferred way?
Does it matter which direction you rotate? Whether it's the one in the front, the one in the back, clockwise, counterclockwise? No.
Okay.
No.
So those energy diagrams can be read backwards to forward?
Yes.
Okay.
Yeah, because we can, of course, go this direction or that direction.
Yeah.
Doesn't matter. In the homework, you considered energy diagrams where not all the groups were hydrogens, and that means that not all staggered and eclipsed conformations are equal. Of course, in the case of ethane, they would be, and that's why I'm not drawing the others, because basically we have 3 identical energy barriers as we rotate around those carbon-carbon bonds. Other questions? Yeah.
So where does the molecule, I don't know if this makes sense, get the energy to go through that transition state?
Great question. Where does the molecule get the energy to go through this transition state? And the answer is from other molecules. Kinetic energy, the molecules have kinetic energy because they're bumping into each other. Higher temperature means they're bumping into each other faster. You can imagine as one of these bumps into the other, they're going to transfer some of the kinetic energy moving around to kinetic energy of rotating bonds. And that's, you can't see that because this simulation doesn't account for collision. But we can, if I turn up the temperature a little bit and we increase the time scale of the simulation, eventually we should be able to see rotation around the carbon-carbon bond. By the way, I don't think this temperature is actually meant to be realistic. So the fact that we're at 1200 Kelvin, I think, we just lost it. The fact that we're at 1200 Kelvin doesn't actually mean we'd be at 1200 Kelvin. But do you see the molecules jumping around enough that occasionally it's rotating around that bond? Yeah. So yes, we're getting the energy to do that from the average kinetic energy of molecules in solution. So one interesting question you can ask is there enough energy at whatever temperature you're at? Is there enough kinetic energy for the molecule to go over this barrier? And we're not going to really worry about that too much, though. If you take 1/2 times, I think it's Boltzmann's constant, but if you want it to be in kilocalories per mole, the universal gas constant will work. And then temperature. And if you multiply that out, that will tell you sort of the average kinetic energy of molecules at any given temperature. And then you'll be able to see whether or not you can easily overcome a barrier. And it turns out that 3 kilocalories per mole is child's play at room temperature, which means methyl groups are just spinning around constantly. Okay? We could calculate that, and maybe I will at some point, and we can figure out what that is. But the idea is that there is enough kinetic energy at room temperature to easily surmount the 3 kilocalorie per mole barrier. All right. Other questions? Yeah.
Would we ever have a Newman projection where there's a pi bond?
Would we ever do a Newman projection where there's a pi bond? You certainly could. So we could do, let's look at this pi bond in ethane. And let's just, I'll leave it to you guys to remember that I really want to draw this as a Sith eye, but I'm not because I'm trying to move forward. Anyway, this is what we would see in the in ethylene. The purple proton here is cis2 or eclipsed with the blue proton in the back. And that's required, that planarity where all the carbon-hydrogen bonds in the front are eclipsed with carbon-hydrogen bonds in the back. That's required by the definition of a pi bond, right? Where we have a lobe, 2 p orbitals on those adjacent atoms overlapped with each other to form a new pi molecular orbital. And that we could draw that orbital here. Sort of this sandwich view. We only get the pi orbital overlap when the carbon-hydrogen bonds in the front are eclipsed with carbon-hydrogen bonds in the back. And if we were to try to rotate around this carbon-carbon bond, let's say by 180 degrees, we could get to, and the question here is, are these two actually in equilibrium with each other in solution? So imagine we can label protons, and now blue proton is no longer eclipsed with carbon hydrogen in the front, purple carbon hydrogen in the front, but is in fact anti to it. And after that rotation around that bond, we could again have a stable pi bond. But the question is, what would the transition state be? And in that transition state, and I think we maybe talked about this last time, in the transition state, the dihedral angle would be 90 degrees. And in that case, the p orbital on the carbon in the front would no longer overlap with the p orbital on the carbon in the back. So here's the p orbital on the carbon in the front. Here's the one on the carbon in the back. They're 90 degrees away from each other. So in order to get from our first conformation to our second conformation, we have to pass through an intermediate where the pi bond is broken. And that's uphill by around 68 kilocalories per mole. So there's not enough energy at room temperature to do that. And that's why we're going to assume, for all intents and purposes, that you can't rotate around pi bonds, and that's why we bothered to do the E and the Z stuff, because they're not in equilibrium with each other. All right? And if we wanted to, we could come back here and let me see if I can find ethylene. There we go. And we're going to turn up the temperature on this, and you're going to see that even still, they're not twisting around relative to each other, right? We're seeing a lot of tumbling in solution, we're seeing a lot of bond vibration, but we're not seeing rotation around carbon-carbon bonds. And that's because in order to rotate around that carbon-carbon bond, you'd have to break the pi bond. All right. So I want to talk briefly about why eclipsed is so much, well, it's not less stable. The eclipse conformation is less stable by a small amount, but we want to talk about why. Some good numbers to keep in mind, by the way, is that in terms of, it doesn't apply here because we're not talking about equilibrium differences in energy. We're talking about energy differences between a minimum and a transition state. But in general, in organic chemistry at room temperature, if you have a difference in free energy of about 1.36 kilocalories per mole, that equals a factor of 10 in equilibrium constant. So, and that will come in that'll come in handy a little bit later, and that's not that important for you to memorize or remember, but I may refer to it. Okay, why is the staggered conformation more stable than the eclipsed conformation? Two reasons, both sides of the same coin. I want you to remember that carbon-hydrogen bonds involve an sp3 orbital on carbon overlapping with an s orbital on hydrogen, and you have two electrons here in that orbital. Maybe we'll use, red for the electrons. And how do we want to say this? In the in the eclipsed conformation, oops, that's an eraser. The carbon-hydrogen bond on the carbon in the front is overlapped with the carbon-hydrogen bond with the carbon in the back. And that generates some electron-electron repulsion. To see this, there's our filled carbon-hydrogen sigma bonding orbital in the front, and then here's the one in the back. And you can see that they would overlap with each other. Okay, so first you get electron-electron repulsion because those pairs of electrons are closer to each other in the eclipsed conformation than they would be in the staggered conformation. And in fact, in the staggered conformation, that's about as far apart as you can possibly get carbon-hydrogen bonds. There is no further apart. Okay, so just distance. The distance is closer when they're eclipsed than it is when they're farther apart, and that's electron-electron repulsion. So electron-electron repulsion is sometimes called steric hindrance or steric strain. I don't know the origin of the word steric, but in OChem we use it to describe how big something is, but it's really a function of electron-electron repulsion. Molecules, groups start to bump into each other for reasons we discussed last time because the electrons repel each other. A related explanation here is what we learned about previously about what happens when you line up filled orbitals. Do you remember we talked about why helium doesn't form He2? And the reason for that is you can overlap the s orbitals in helium to make a sigma and a sigma star, but the fact that both helium s orbitals are filled means that when you mix them together, you're going to fill both the bonding orbital and the anti-bonding orbital, and that leads to overall destabilization. There's no bond, right? In a similar way, when we have two filled orbitals line up with each other like this, there is mixing of those orbitals together, and that ends up taking one electron pair, a little bit lower in energy, and then one quite a bit more higher in energy. That's called closed shell repulsion, but the basic idea here is you don't want filled orbitals to line up with each other because then you get destabilization. It's basically the same thing as electron-electron repulsion, steric hindrance, and steric strain, all right? Yeah.
So it's because of the anti-bonding orbitals are being filled and something like that?
Yes, if conceptually you imagine mixing, if you conceptually imagine mixing this sigma bonding orbital in the front with the sigma bonding orbital in the back, and both of those are filled, you're going to get a new molecular orbital that's lower in energy and another that's higher in energy that's filled, and that's unfavorable. All right? Okay. So that's side one of the coin. Side two of the coin is that in the eclipsed conformation, you've got, in addition to avoiding repulsive overlap of filled orbitals, you also have favorable overlap of a filled sigma bonding orbital with an unfilled anti-bonding orbital. So here is the carbon-hydrogen sigma star anti-bonding orbital. And it is empty. And then you have the carbon-hydrogen sigma bonding orbital that is filled. Okay, and we could draw this on a Newman projection. Here is the carbon-hydrogen bond in the front, and its sigma bonding orbital that is filled overlaps with the sigma star on the back carbon that came from the anti-hydrogen. Okay, so here's the node in the back. This is the empty sigma star, and this is the filled sigma. So when a filled orbital lines up with an empty orbital, as we have seen before, you can get a mixing of orbitals that can make the electrons in the filled orbital move lower in energy. So let's just imagine here is the sigma star, here is the sigma bonding orbitals. The sigma is filled, the sigma star is empty. When you mix them together in energy, the sigma bonding orbital moves lower and the sigma anti-bonding orbital moves higher. So the electrons in that sigma bonding orbital by mixing with the adjacent sigma star actually get to move lower in energy. This concept, overlap of a filled orbital with an empty orbital in the same molecule with an adjacent empty orbital, is called hyperconjugation. And we use it as a concept to explain some of we use it as a concept added to valence bond theory to explain some of the conclusions that molecular orbital theory gives us. The consequences of hyperconjugation are, first, this energy stabilization. The electrons in the filled orbital are stabilized. They move down in energy. The second consequence is the electrons in the filled orbital spread out a little bit toward the empty orbital. And consequence number 3 is the empty orbital spreads out a little toward the filled orbital. All right, so you can imagine these electrons, and it's not, the reason it's called hyperconjugation is it's not a full-on bond. Regular bonds are, if it's a pi bond, it's like 68 kilocalories per mole. If it's a carbon-hydrogen sigma bond, it's like 85 to 100 kilocalories per mole. This effect is small. It's only a tiny, tiny, tiny fraction of an actual bond, but it is noticeable. The electrons in the carbon-hydrogen bond move down in energy a little bit. They also spread out a little bit towards the other carbon. In the same way, this empty orbital actually spreads out a little bit towards this carbon-hydrogen. Yeah?
Would that drag to move the hydrogens a little bit towards the opposing side?
Would that move the hydrogens towards the opposing side? Well, that's difficult to say in the sense that you can't, in nature, turn this effect on and off. So you can't see what it would have been without it. Yeah. Go ahead.
So wouldn't using the anti-bonding orbital lead to breaking the bond?
So wouldn't using the anti-bonding orbital lead to breaking the bond? And the answer is yes, if the overlap was good enough and close enough. You'll see that the more, when you mix two orbitals together that are close in energy, the bonding orbital goes down a lot and the anti-bonding orbital goes up a lot. When you mix together two orbitals that are far apart in energy, the mixing isn't nearly so good, and that's why you can think of hyperconjugation not as actually a full bond, but as making the sigma star actually go higher up in energy and making the sigma go lower in energy. So that sigma star is still there. It's just been moved up higher in energy. Yep, but the fact that it's moved up higher in energy doesn't matter because it doesn't have electrons in it. Okay. Hyperconjugation, overlap of a filled orbital with an adjacent empty orbital. The electrons in the filled orbital are stabilized because they move down in energy. The empty orbital is destabilized, but it doesn't matter because it's empty. The electrons in the filled orbital spread out a little bit in this direction, and the empty orbital spreads out in the reverse direction. So this is the other side of the coin, why eclipsed is more stable than staggered. And frankly, it's easy to... Whoa, let's rewind and rephrase that. That's hyperconjugation is the other side of the coin as to why staggered is more stable than eclipsed. Staggered is more stable than eclipsed. Now, that point is easy to memorize. And it's also easy to memorize, well, it's because of sterics and because of hyperconjugation. So there's not that many interesting questions I can ask about this effect. But hyperconjugation ends up being really important in a lot of reactions that we're going to discuss. So let me give you just one example. And this is an example that won't make a huge amount of sense until we get to chapters 7 and 8. All right, so here is a carbocation, and there's an adjacent carbon, there's an adjacent methyl group. What would you say the LUMO of the carbon, of this carbocation is? The empty p orbital that's on which carbon? The positively charged one, right? Okay, good. And we will see that that's a perfectly reasonable and useful prediction. And if you had a nucleophile with high energy electrons or something, where would it attack? It would attack at the p orbital, and you would have a filled orbital on the nucleophile mixing with an empty orbital on the electrophile, and you would get a new bond. Okay. However, sometimes, depending on the identity of the nucleophile, we get something else entirely as a product. Where did that come from? Well, sometimes, depending on the identity of our nucleophile, what happens is the nucleophile attacks the hydrogen, breaks the carbon-hydrogen bond, and these electrons kick down to form an alkene. Okay, I mean, in terms of electron pushing, we can see where the bonds come from, but what the heck? I thought HOMO always attacked LUMO. And the reason why this occurs is because some of molecular orbital calculations show that some of the LUMO is actually out on the nearby hydrogen. So that a nucleophile will have to decide, do I attack the hydrogen or do I attack the carbon? Now, there is a reason why I've drawn the phase relationships like this. It's not very important for this class, so you don't have to worry about it. If you want to know more about it, you can come talk to me. But the results of MO theory, if you were to calculate the LUMO here, you would see that some of it is out on those adjacent hydrogens. How do we explain that with valence bond theory? With MO theory, you can explain it easily because MO theory lets go of the concept of bonds completely. But we don't want to do that because it's confusing. So what we will do to get to that conclusion is we will add hyperconjugation to valence bond theory. We will say, for example, as we look at that carbocation, that the electrons in the carbon-hydrogen bond are lined up with the empty p orbital on the adjacent atom. What that leads to is, in the plus combination, that leads to the electrons in the carbon-hydrogen bond donating into the empty p orbital, and they get to spread out and move lower in energy. But at the same time, we also get the minus combination where the LUMO, the empty p orbital, actually spreads out onto the hydrogen. What I'm showing you here represents these lower energy electrons. What I'm showing you here represents this higher in energy empty orbital. Okay? So because of hyperconjugation, some of the LUMO is on adjacent carbons. I'm sorry, on adjacent carbon-hydrogen bonds. All right, so we'll come back to that again, but this is the reason why we're talking about it. We want to introduce it as a concept because it's going to be really useful in getting us to the conclusions of high-level mathematical calculations without actually doing the calculations. Go ahead.
Just to clarify, is this on all those carbon-hydrogen bonds or just the one that's eclipsing?
So is it with all of the carbon-hydrogen bonds or just the one that's eclipsing with the empty p orbital? It's more on the one that's eclipsed, but actually it's also on the others that can partially line up. But it's fine if we ignore that. So yes, I'm oversimplifying. Actually, the LUMO looks like this. By the way, if you squint and look at that at the side, it almost looks like a pi star a little bit. But that's beyond the scope of what we want to do in this class. But it makes me excited to notice. So anyway, and this one looks almost kind of like a pi bond, but again, this effect is weak and it's only worth about 1 kilocalorie per mole per orbital interaction. And in the staggered conformation, you have 3 such hyperconjugation interactions between a filled carbon-hydrogen bond and an empty sigma star. The same thing would be true for this proton here and the one that it's anti to. Same would be true for this proton here and the one it's anti to. So overall, it's about 3 kilocalorie per mole stabilization. And you have to break that interaction to rotate around the carbon-carbon bond, and that's the barrier that we're going through. All right. So let's pause there. When we come back, we're going to talk about putting other stuff on this molecule instead of just hydrogen.